Perfect. Yeah, welcome to my talk on block preconditioners for moving domain fluid dynamics coupled to physics and projection-based reduced models. I'm Marc. I'm currently a postdoc at MOX in Milano, at Politecnico Milano, but this is work I've done actually with David Nordstetten back in my time at King's College in London, and he is now at University of Michigan in the US. Okay, what's the general scope? So fluid dynamics for the cardiovascular system is a deal. Fluid dynamics in general serve as a valuable tool to assess patient-specific blood flow in the cardiovascular system. For example, you solve 3D incompressible Navier-Stokes equations either in a fixed or in a moving reference frame, depending on if you maybe have some information on the boundary motion or if you want to do fluid structure interaction, for example. Here you would see an aortic arc where you would be interested in the blood flow, for example, which comes here from the left heart and goes here up and down in the descending aorta. So one big aspect is that the up and downstream vascular architecture is not fully modeled as three-dimensional region, and often you use some kind of so-called lump parameter models in order to represent so the traction which stems from sort of the flux at this boundary. And these lump parameter models, they typically impose a pressure-dependent or flux-dependent pressure, and they are sort of non-local nature, and we will see why this can be a problem in general when coupling these. Another approach would be to include the elasticity of the deformable wall. So if, for example, you could do full FSI, but you then have also a big computational cost possibly. There are also reduced dimensional approaches around, reduced dimensional wall models. For example, the coupled momentum method or the fluid reduced solid interaction method, which we propose, where you actually use a Galerkin ROM for the wall. So the challenge will be the design of solvers and preconditioners for Navier-Stokes coupled to these kind of models of non-local nature. What does non-local nature mean here? For example, consider a lump parameter model. There you have in the weak integral of the Navier-Stokes equations, you will get this kind of term here, a pressure which is integrated here over the surface. But the pressure itself would be some function of the flux, which is also an integral over the surface. So you actually, if you do it in a naive way, you just integrate this like this in your momentum equation, you will get a double integral in your boundary term and would actually get some very dense blocks in your fluid system matrix depending on the sizes of these kind of reduced boundaries. The other approach, for example, if you consider a projection-based wall model and a Galerkin ROM, you would have a similar issue where you would then, because you only project some degrees of freedom, for example, or the wall of degrees of freedom, you would get these very narrow bands in your system matrix which reach out far from the diagonal. So what is the problem there? If you want to design preconditioners, you would then have some potential ill conditioning for this fluid system matrix here. And the idea would be here, what we want to propose, some optimal preconditioners which deal with these kind of models of non-local nature. So just a short recap for standard fluid dynamics without any reduced models, just considering a preconditioning approach here. So you would have the weak form of the momentum equation and the conservation of mass equation. And then you would end up with this discrete linear system to solve the momentum and the continuity, which you want to solve in a monolithic approach, for example. And what you can do here, you take some stationary iteration like GM-West, for example, and a preconditioner could be based on the exact block factorization of this matrix with the Schur complement here. And what is typically done here is using, for example, the simple method, the semi-implicit method of pressure-linked equations, where you would approximate your matrix, this block inverse like this, for example. So this would also be available in Petzy's field split if you specify, you can somehow specify it at least in Petzy's field split, or you can implement it just as an action of sort of this matrix inverse on a vector X with the output vector, a vector Y. So you would first do an A solve, then you would compute the update. You would solve this modified Schur complement where you only have the diagonal of A inverse because you don't have A inverse normally. Do another update, and then in the end, you can also do a diag A inverse update to get the final velocity. You could do another A solve, but this is actually not really needed. As far as I've experienced, this diag A inverse update is fully sufficient. So what if we now have these kind of reduced models? And now we consider, for example, this pipe, and it's connected to a reduced model. The flow can leave, for example, here and can enter back into the domain again. So in order to not get these dense blocks, one approach to couple these reduced models is via a multiplier constraint. So you get a third equation and would have this kind of capital lambda, which is a pressure stemming from the reduced dimensional model, which you would have need to do a subsolve to get this depending on the complexity of your reduced model. So what you end up with then is a 3x3 block system where you solve momentum continuity and the constraint equations. And if you didn't do it like this, if we go one step back with a naive approach of the dense entries you would get, you would end up with this 2x2 system again. And here, especially because this zero-dimensional model is again linked between two boundaries, you would get two additional blocks, and this is totally detrimental for any AMG solver you want to do on this block. But with a 3x3 system, you actually move these contributions to a tiny matrix R and get only these couplings in these D blocks, right? So this is only the 3x3 system matrix. We haven't proposed a preconditioner yet. This is what we want to do in the next step here. So why don't we just follow the same structure like for the 2x2 system, that we actually do a block matrix factorization and then propose an approximate inverse to this 3x3 matrix. And you get some of the multiple of these Schur complement-like matrices, which we again approximate with the diagonal of A inverse. The nice thing, you can also implement it with in PETSI with the Python context, and you can just implement these solves. Again, you do the A solve, the update, the Schur solve, another update, and then this solve is actually a very cheap solve because it's only a very, very tiny block. It's only the reduced models, actually, this very lower right block you've seen. So this can be done with a direct solver again. Then you'd use again, do another update, solve for the Schur complement again, another update, and the diag A inverse update. So what's sort of the cost compared to the other approach? You would move from two expensive solves, so the A solve and the S solve for the 2x2, to two S solves and one A solve. So it's not that much more of a deal, I would say, because the W solve again is a very, very cheap one. And you have the flexibility of also designing these A or S solves. For example, you can use AMG preconditioned GMOS, or you can just do one AMG sweep, for example, so just apply the sub preconditioner once, depending on how good your inverse should be and how challenging your problem might be. So just a test example here, which we have some strong scaling results. We actually here compared the package Mbit, which is a Phoenix X-based open source solver tailored towards cardiac mechanics, with another proprietary Fortran code, same implementation in two different environments. Of course, the backend is always PETSI, and you see similar performance here, some speed up tests for this pipe flow problem. And here we also did a comparison for this kind of red line. This is sort of a weak scaling from 2 cores and a relatively coarse mesh to a fine mesh with 72 cores. And the red line would be actually the naive approach, not splitting, doing the 3x3 split, but just implementing the zero-dimensional model directly into the main block matrix with these dense blocks. And there you see that it massively goes up the computation time. So it's very, very expensive. AMG works on this structure, but it takes ages to really form this the correct AMG pattern. So now we move on to ALE fluid dynamics and coupled to some reduced dimensional wall models, which I've introduced before. So what we are interested in here, again, the weak momentum equation in ALE description, so and the conservation of mass. Again, the coupling constraint to a 0D model, also written with respect to this moving reference frame. We would also have the domain motion now, because this you also would have to account for the moving domain, and the domain motion problem can be some dummy linear elastic solid, for example, and it gets the Dirichlet boundary condition, the fluid displacement on the boundary. That's typically what you do in FSI. And here you again have the traction from the zero-dimensional model. You have now a reduced dimensional solid model on the boundary. And additionally, it's not shown here because it's not the main topic of the talk, but this is actually additionally projected to a lower dimensional subspace. It's actually a Galerkin ROM. So the boundary velocities are in a lower dimensional subspace. You have from, for example, modes you generate from imaging data or some other high dimensional model. So what do you have here? If you rearrange a bit, you have a 4x4 system matrix. And you see, okay, this was the submatrix from before, the 3x3 fluid plus 0D submatrix. And if again here take a naive approach and don't do anything, like we've seen before, we get this is a 3x3 matrix. We moved the 0D model already out, right? But we still get these bands from the Galerkin ROM. And you also see here on the pressure blocks, because a few velocities depend on all the pressures and vice versa. If you now form the Schur complement, you can't even allocate the memory anymore. So at least on a normally sized system. So this is actually also an issue, but you can do a little trick by because the ROM is also only a few variables, right? You can just group them together with the 0D model, and then you rearrange the matrix, and you get this kind of system here, where you move the ROM out of the A block, and you can then easily deal with it again. Another example, so of course we still have the AL domain motion problem, and there we could embed this 3x3 block preconditioner I've introduced before with this kind of forward block Gauss-Seidel method. Yeah. So you do first the ALE grid solve, then you compute this update, and then you apply the 3x3 block preconditioner we've shown before. And this is just an example of a flexible pipe where we have one POD mode actually, so on the lateral surface, so it can only deform in this radial direction. We have a pressure boundary condition, and we connect it to some resistive model. And there we see again this kind of strong scaling and iterations over the whole simulation time for 3 different meshes. Of course, if you refine, you also change the physics a bit. You need a little bit more iterations, but still it converges pretty nicely in 3 nonlinear iterations. Actually, each step also. Okay, then the last application would be FRSI in the left heart, and this is actually an example where we have a time series of images, and we generate a sort of a POD subspace out of this displacement field we can extract, and then construct our reduced dimensional wall model, and then we can also assign some elastic, viscous, and active properties also, both for the atrium and the ventricle separately, and we can really simulate a full contraction here. This also works nicely by just there I made actually use of Joe Dean's mixed Dolphin X branch, because I want to model these valves, and I just split my pressure space only at these valve planes, and I can sort of model a discontinuity there also. And you see that the solver performs also very, very well. Even for the very fine mesh, you actually get less linear iterations over time compared to a coarser mesh. So it behaves pretty nicely for further refinements. This brings me to the end of my talk. We propose a new 3x3 block preconditioner solving Navier-Stokes coupled to reduced models of non-local nature, either for Eulerian fluid dynamics or ALE fluid dynamics. We have some flexibility with respect to the inner solves and the approximation of the Schur complement. But there are some limitations, which is generally known when it comes to the Schur complement approximation, especially for highly convection-dominated flow. And so there are maybe some synergies to leverage to really try to find a different approximation for the Schur complement to maybe for highly convection-dominated flows to have a good performance there. But for these problems, it worked actually very well. So this is also openly available in this package mbit, which you can find here on GitHub. And yeah, thank you for your attention, and I'm happy to answer some questions.